Okay, so good day everyone. So our topic for this morning is about water treatment reactor tank design. So I will show to you the basic wastewater treatment plant for you to picture out what happened in a wastewater treatment plant.
Cities and towns have sewerage systems in place to carry the wastewater from our homes, hotels, factories, and other establishments to a sewerage treatment plant where the wastewater is treated. It is then deemed safe to release into other water sources. The treatment of wastewater goes through different stages. Wastewater is treated to remove the physical, chemical, and biological contaminants present in it through various processes. The pre-treatment process involves the sewage being sent through grids or vertical bars that can remove large solid substances like metal cans, paper, and plastic materials. In primary treatment process, the sewage flows through the grid chamber very slowly so that the sand, pebbles, and soil settle down at the bottom. The sewage flows into the settling tank or sedimentation tank, where the solid wastes like feces are allowed to settle down. Wastes such as soaps, oils, and grease rise to the top of the wastewater. The waste material that settles down at the bottom is called the sludge, and the floatable material is called the scum. Scum is then removed using a skimmer, and sludge is removed with a scraper every few days. The water that is left out is called the clarified water. In the secondary treatment process, biological or organic wastes are removed. It is a biological process. This is done by transferring the clarified water into an aeration tank, where air blowers bubble air, which helps the aerobic bacteria to grow and feed on the organic contaminants, such as food waste, feces, and other organisms. The mixture then flows from the aeration tank into the clarifier, where activated sludge settles out by gravity. The activated sludge so produced along with the sludge produced in the primary process is transferred to the digester, where it is decomposed by anaerobic bacteria. Biogas is produced in this process, which can be used as fuel or can be used to produce electricity. The activated sludge is then left in the sand drying beds. Some quantity of water in the activated sludge evaporates, and the remaining quantity drains through the sand beds. This leaves behind the remaining dried sludge, which can be used for making fertilizers or compost. In the tertiary treatment process, the leftover wastewater is treated with chlorine to remove the phosphorus compounds, nitrogen compounds, and bacteria. It is a chemical process. Chlorine tablets are added to kill the germs. This process is called chlorination. Then this water is let off into the water bodies.
Hey class, who would like to do problem 3 on the board?
So we have here the slide. I will read the slide first. The 10 state standards set the criteria for sizing of tanks, including detention time, overflow rate, wear loading, and velocity. So by which the detention time is T equals the V over Q, unit of hours. So by which your V is the basin volume, your Q is the average daily flow. And the overflow rates, sometimes the terms get interchanged with hydraulic loading or with the surface loading. So noted as V sub O is equals to Q over A. So your Q is the average daily flow, and your A is the surface area of the settling basin. And for the wear loading, W equals to Q over L. Your Q is the average daily flow divided by L, which is the length of the weir. Is it an example of detention time and hydraulic loading? So the problem states that you're going to calculate the detention time of a tank that is 20 feet in diameter, 10 feet with a deep flow rate of 50 gallons per minute. And what is the hydraulic loading rate in gallon per day feet squared? So again, we're going to determine the detention time T sub D and the hydraulic loading Q sub O. So to solve for the detention time, so that is equal to T sub D equals to V over Q. So here we have a circular tank. So how do we know that it is a circular tank? Because in the problem, as stated here, the given is the diameter, right? So the area of the, of course, the circular tank is pi r squared. But we know that the diameter is equals to r over 2. So if we're going to square the r, so that is 20 divided by 2 square all over, or equal to pi 20 feet squared over 4. And we're going to multiply it with the depth of the water or the tank. So that is 10 feet. So that is the volume of the tank. Divided by the flow rate, 50 gallons per minute. So we need to convert here on the numerator from feet cubed to gallon. So 1 cubic feet is equal to 7.48 gallon. So that we can cancel out the gallon here in the numerator with the gallon unit here in the denominator. And also we convert the unit of time, 60 minutes, 1 hour, so that our final answer will be 7.8 hours. And for the hydraulic loading rate, Q sub O equals to Q over A equals to 50 gallon per minute. Again, convert into unit of day for the times, since that is what is asked in the problem. So this is the conversion, 60 minutes, 1 hour times 24 hours per day. Cancel out minutes, cancel out hours. So what is left is gallon per day. Divide by the area. So pi d squared over 2 squared. So we arrive at Q sub O equals 221.9 gallon per day feet squared. So another problem with regard to sedimentation. So the sedimentation portion of the inline treatment plant is to be designed. The proposed design for the sedimentation tank is 140 feet wide, 280 feet long, and 17 feet in depth. The length of the effluent weir along the 4 channels at the end of the tank is 1,260 feet. Calculate the major parameter used in sizing this unit based on the design flow of 40 million gallons per day. So again, what is asked in the problem is the detention time, overflow rate or the velocity of effluent water, and the weir loading and the overflow rate. So to solve for the detention time, so that is equal to V over Q. So it's very obvious stated here in the problem that the tank is rectangular, since the given dimension is the wide, long, and depth of the tank. So we are going to multiply 140 feet times 280 feet times 17 feet all over, divide by the Q, which is equal to 40 million gallon per day. And we're going to convert million gallon to cubic feet. So we're going to multiply the denominator with 1 CFS or cubic feet per second divide by 0.6463 million gallon per day. So this is the conversion unit here. And we arrive with an answer of 10,767 seconds, or in minutes of 180 minutes. Okay, so for the letter B, for the velocity, so V is equals to Q over A. So Q here is 61.9 feet cube per second. So how we arrive this one? We arrive this one by 40 mgd multiplied by 1 CFS all over 0.6463 mgd. So if we execute this one, this is equivalent to 61.9 cubic feet per second divided by the area. So the area, so dimension of the area is the depth of the tank multiplied by its wide. So that's equivalent to 0.026 feet per second. And for the weir loading is equals to Q over L. So it is given that the flow rate is 40 million gallon per day divided by 1 to 60 feet. So that is equivalent to 31,746 gallon per day per feet. And for the overflow rate, that is equal to V sub O equals to Q over A. 40 million gallon per day divided by the area of by which we use the 140 feet wide multiplied by the 280 feet long. And that is equivalent to 1,020 gallon per day per feet squared. So rapid mixing occurs in coagulation or in flocculation tank. So you need to disperse chemicals in the tank so that there will be reaction between the coagulant and flocculant and the suspended particles present in the water. In a way, they will form flock or clumped, and in a way, they will become bigger and denser than water, and they will settle down. And here we're going to estimate the volume of the tank using this equation. G T sub O equals to 1 over Q square root of PV over mu, where G is the mean velocity. So for example, 900 to 1000 per second. Your Q is the flow, your P is the power requirement, and your V is the tank volume, and your mu there is the dynamic viscosity of water at 60 degrees Fahrenheit. So that is equal to 0.0023. So for this example on rapid mixing, we're going to calculate the volume and dimension of a rapid mixing tank with a flow rate of 5 cubic feet per second and a mixing time of 10 seconds, a mean velocity gradient of 1000 per second, and a power requirement of 200 pound-feet per second. The water temperature is 60 degrees Fahrenheit. So what is required in the problem again is the volume and the dimension of the mixing tank. For this example about rapid mixing, we're going to calculate the volume and dimension of a rapid mixing tank with a flow rate of 5 cubic feet per second, or CFS, a mixture time of 10 seconds, a mean velocity gradient of 1000 per second, and a power requirement of 200 pound-feet per second. The water temperature is 60 degrees Fahrenheit. To compute for the volume, we are going to use this equation. GT sub O equals to 1 over Q square root of PV over mu. So your G is 1000 second, your T sub O, your mixing time is 10 seconds, and your Q, the average daily flow, is 5 cubic feet per second, square root of the power, 200 pound-feet per second. And your volume here is the unknown. All over this, divided by the viscosity of water at 60°F. So, by algebra, we can extract the value of V equals to 288 cubic feet. And to calculate for the dimension of the tank, so we have computed that the volume is 288 cubic feet. So this is a rectangular tank, so we're going to find the cube root so that we can solve the dimension of the tank. So if we set the dimension of the tank should be a whole number, so we're going to run up, so that is 7 times 7 times 7 feet. So that is 343 cubic feet, which is larger than 288. So we'll again adjust. So by using 7 feet times 7 feet times 6 feet, we arrive at a maximum of 294 cubic feet, which is higher than 288 cubic feet. So by estimation, we can therefore arrive or conclude that this is the dimension of a rectangular tank. Okay, so for the flocculation tank is our next example. Determine the volume and depth of a circular flocculation tank that is 10 feet in diameter and need for highly turbid water that has an average flow of 1,000 gallons per minute, a velocity gradient of 100 per second, and a GTO of 120,000 seconds per second. Again, the unknown is the detention time, the volume of the flocculation tank, and the depth of the water, D. So to solve for the flocculation time, the T sub O is equals to GTO over G. So GTO is given 120,000 seconds per second over your G, which is 100 per second. And we're going to convert the unit of time here to minutes, and we arrive at 20 minutes for the flocculation time. And to solve for the volume of the tank, so we have here the equation V equals to QT. So your Q is the average daily flow, 1,000 gallons per minute, multiplied by our time that we have solved previously, 20 minutes. And we're going to convert the gallon unit to cubic feet. So that's why we divide all over to 7.48 gallon per cubic feet, and we arrive with a volume unit of cubic feet, which is 2,674. And for letter C, we're going to find the depth of the tank. So the volume is equals to area times D, the depth of the tank. So your D equals to V over A. So the volume, 2,674 cubic feet, divide by pi D squared over 4. So which is 34 feet as your final answer. Okay, that's it for today. Thank you, everyone.